Okay, welcome to lesson 15. So we're going to start talking about experiments, how we design them, what we hope to get out of them. Going to mention some working variables and confounding variables, as well as get into some popular designs. So introducing comparative studies. So the idea is now we want to compare some quality between two or more groups. A lot of times we'll start at two, but then we'll increase how many we're looking at. So by quality, I mean maybe you want to compare averages, maybe you want to compare medians or proportions, that kind of thing. So the example we're going to start with, we have a manufacturer, they make rubber seals, and we are interested at looking at the average strength of seals. Specifically made across 4 different machines. So we've got machine 1 and it's producing rubber seals, machine 2, machine 3, and machine 4. And we want to go ahead and compare the tensile strength across the machines. So we would want to identify the factor for this study, the treatment, the experimental units, and the response. So just going to throw these out. So the factor, it's a characteristic that differentiates each group or population. So here, my factor is going to be machine. And treatment, a lot of times they're going to be like levels of that factor. So the treatment is a combination of factors and or levels of factors. So what makes each group different is what machine it is, but then treatment, it's, I'm going to put M1 for machine 1, machine 2, machine 3, or machine 4. So those are my levels. I have 4 levels. Experimental units. So experimental units are the smallest units that you are applying a treatment to. So you could think of this as you are applying, each rubber seal is being made like from one machine. So the individual rubber seals. Oops, I can spell individual sometimes. Rubber seals. I can't spell, apparently, at all. And so it looks like there's 5 from 4 machines. There's 20 of them, 20 experimental units. And then my response. My response is going to be, what do I actually measure from each one? So what is that measured outcome that I measure from each one? Absolutely asking yourself what is the response moving forward is going to be super helpful. It tells you, am I looking at an average? Am I looking at a proportion? Hey, what kind of test am I looking at? Knowing what you're actually collecting from each individual in the data set, super important. So my response is going to be the tensile strength, whatever units those are in. And I know we have that posted somewhere. Tensile strength, that's what we record from each one of the rubber seals. There is a note here, so the measured outcome from each of the observational units, it could be different than your experimental units. In this case, it's not. But things to note, so maybe I have 2 tanks and I give 1 type of fish food to each tank. And then I measure the weight of fish in each tank. The experimental units are the tanks because that's the smallest individual that I apply them at. I didn't apply them to individual fish. It's way too hard to force feed individual fish. But then my observational, I actually observe the weights of individual fish. So keep that in mind. Most of the time we prefer, it's simpler if we have observational units and experimental units as the same. But there are instances where they're not, absolutely. So an observational study, this is more basic. You observe. So you observe and collect information on units. However, you're not attempting to apply any sort of treatment. You are strictly observing. So if this person smokes and gets cancer, you are observing, but you're not saying you smoke and then watch them. So you're not applying any sort of treatment. So this is useful when you want to compare groups, especially across demographic groups because you cannot assign this. Like, you can't assign, okay, well, you're male and you're female. It's considered highly unethical. So you might observe, hey, I saw this difference between these 2 or 3 or more groups, but you can't actually assign people to individual groups like that. It's useful for exploring association, but not causation. Causation, we really only want to talk about when we have a well-designed experiment. We'll go into what that means. And especially when you have retrospective data. People might say, oh, this event occurred. How, is this tied to this thing? A lot of times it's useful to use a retrospective observational study. Also, before we go away from there too, is another time it's really useful for an observational study is when the differences between the groups is unethical. So suppose you want to explore how the effect of smoking on a 10-year-old's lungs. Well, guess what? Nobody ever is going to let you round up a bunch of 10-year-olds and assign half of them to smoke, right? So you can find individuals that do smoke and observe from there, but you cannot ethically assign that. Lots of studies, like smoking and cancer is a really popular one. Drinking and the effect of on a fetus for pregnant folks. That's another one. Super unethical to take a pregnant person and assign them to drink or something that you think is harmful. So observational studies, they're your go-to in those scenarios. Issues though, we really cannot say from an observational study alone that, hey, we have this cause and effect relationship. It's really hard because you didn't do it in a controlled setting like an experiment. You can have unaccounted for lurking variables. So that could be a variable that's associated with the response, associated with your explanatory variable, or maybe both. And it's usually the lurking variable is a variable that you don't collect information on that could be impacting your results, but you don't have that information. So one fun example, does cheese cause degrees? So it looks at 10 years of civil engineering degrees versus mozzarella consumption in the US. So as you can see, cheese consumption going up, civil engineering doctorates awarded going up. Obviously, if we eat more cheese, we get more doctorates, right? Maybe there's something else going on there. So you don't want to say, hey, this causes that. Absolutely not. You might say, hey, there's an association, but you don't want to say one caused the other. In fact, it's really hard to even tell which one causes the other. Maybe getting doctorates causes people to eat more cheese. I mean, it probably doesn't, but things to consider. There's no way of knowing which order things go in, or if one is actually impacting the other that way. So experiments. So this is our happy place when we can get a well-designed, and we'll go into what exactly I mean by well-designed experiment. Then we can have cause and effect relationships. It makes a lot of aspects of the write-up so much cleaner and more pleasant. It's delightful, but not always practical. So the idea is you have your sample and you have 2 or more treatments and you randomly assign each individual in your sample to one of the treatments. So you randomly assign them to their treatment group. And in this sense, because you randomly assign them to their groups, what you did is, in the long run, you made the most prominent difference between any of the groups just which treatment group they're in. If you can basically make it so that, hey, this group is as similar to this group as possible, except for the treatment they got, you can then conclude that the treatment is what caused the difference in the response. Absolutely love them. So comparing controlled groups in a randomized experiment, absolutely very, very important, especially when people, they want to maybe change protocol, maybe they want to honestly, experiments are used everywhere. You might go, hey, I want to know, is this machine better for blank? And you would compare it to the old machine and that sort of thing. People use it for money saving or life saving things all the time. Oh my goodness, the experiments going on right now with COVID, like so many. But yeah, definitely you usually will go to an experiment when you want to get at a cause and effect relationship. So the idea, though, like I said earlier, is that you have gone ahead and you've made the two groups as similar as possible by randomly assigning them to a treatment group, with the main difference being the treatment. So then you can attribute whatever differences you see to the treatments. That is the idea. So some principles of experimental design. So we're really into replication. And I really want to make sure I'm explicit about what we mean by replication. So replication is when you have more than one experimental unit per treatment. What this means is you have 2 or more per treatment group. We want you to have more than 1 per treatment group, right? Because if I end up doing a study and I said, hey, look, I, increased white blood cell count in this cancer patient and basically made them effectively whatever, but there's only 1 person in my treatment group, people are going to look at me funny and go, but why? Why did you only do it for 1? It really adds a lot of validity to have that replication. So it's really, really important. It's not the same as repeatability, where somebody does the experiment over on their own and they test and see if they get similar results. Replication is specifically you have at least 2 or more in each treatment group. That's what we mean. That way we know that we can really attribute hey, this difference I saw really is the treatments. It's not just some fluke. Because if there's only 1 in your treatment group, how do you know it's not, maybe it was just some freak chance. Or maybe it was because this treatment causes this thing. The next one, randomization. So this is that random assignment of treatments. So this is really, really important. This is the basis for us being able to attribute cause and effect relationships. So randomization is really important. It's okay if you want to say they randomly assign the treatment. That's fine too. They mean the same thing. So the idea is you have your subjects and then you randomly assign which group they go in. That's the idea. It helps reduce bias. It makes the 2 groups as similar as possible, making the treatments themselves the main differences between the 2 groups. And then another attribute that's really important in experiments, controls are really, really important. So it gives this is like a reference or base group to compare to. So it helps you understand hey, this treatment A does this, treatment B does this. Well, how do they compare to, no treatment? Or it totally depends though. Ethically, if I wanted to, maybe I had a new cancer treatment, and I wanted to see how it does. I would have my new cancer treatment, but your control is not allowed to be nothing. If there is a known treatment, you cannot deny it. Ethically, that is super unsound. So my control would be whatever existing cancer treatment already exists. That's the idea. But absolutely, in some cases, if it's not, a risk to life and health, you are allowed to make the control effectively nothing. A lot of times we'll talk about having a placebo, so that they don't know they're getting nothing. But one time I had this group of 4th graders that went through this it wasn't a physical ed program, but it was a physical fitness program. And they installed all of this new hardware and they had some training for the teachers there. And what they did is they collected data at the beginning of the year and at the end of the year, and they compared, hey, look at this improvement that we saw in these fourth graders at this school. The problem was they were measuring things like, I don't know why they had pull-ups on there, but they had push-ups and mile times and just a handful of how many step-ups could they do. And they didn't account for just natural growth. They didn't have any sort of control group. They didn't have a group of fourth graders that didn't complete the program to compare to. So we were able to show that they improved, but we weren't able to show that the improvement was due to their program. So it can be very important to have a control group. And one last thing, I want to acknowledge this little blurb here on the bottom. Take it with a grain of salt, though. This phrase, statistically significant, is becoming more and more like a swear word in the field of stats. When you're able to conclude, hey, there are differences among these treatment groups, and it's highly unlikely that this would have happened just by chance if there wasn't an effect of these treatments. We use this phrase, statistically significant. I'll poke at it some more, but just know that it means that the effect we saw is super unlikely to happen just by chance. It's almost definitely because something's going on with the treatments. So now we're going to look at some experiment designs. So we have a couple that we're going to look at. The first one is going to be completely randomized design. Some people will even abbreviate CRD. Not as often, not lately, but completely randomized means I have all my experimental units, and then I'm going to say I have 2 treatment groups. I'm going to randomly assign half to one treatment and half to the other. So random assignment, not personally like me saying, oh, okay, put the first 10 observations here and the second 10 observations here. That would not fly. So they are randomly assigned to their group, and then group 1 gets treatment 1, group 2 gets treatment 2, and then you go ahead and you measure whatever your response is and you compare them across the 2 groups. Like, hey, did I see a higher average in this group than that group? That kind of idea. So completely randomized, just you have all of them and then you randomize from there. So for example, we want to design an experiment. We were looking at tomato yield. I do not know what tomato yield is measured in. It might be weight. That's actually very likely. But we have 10 tomato plants, and we are either going to give them some sort of chemical solution, or we're going to give them nothing and just see how this impacts their yield. So factor. So it will just be that chemical treatment. So specifically in that the treatment or factor levels is going to be they either got the chemical solution or nothing. So basically they either applied a chemical solution or they didn't. Then what did they apply them to? So experimental units is saying, okay, well, what did we apply them to? Hopefully, these 10 plants should all be in their own container. That is important. It gets way, way more complicated if they're not. So the individual tomato plants. And there are 10 of those. And the response, this is getting at, what did we collect from? So we have these tomato plants. They each got a treatment. You could even consider the lack of treatment a treatment. And then what did we collect? And that we collected the tomato yield of each plant. So that would be my response. Absolutely, you can get more specific. Maybe this is in grams. Maybe it's in something else. Maybe it's a number of tomatoes. That would be weirder, but it's most likely a form of weight. But there are a lot of things you could use probably for yield. So draw a possible experimental flow diagram. So I'm going to have my 10 tomato plants here. It's going to look very, very similar to that last slide. So I have 10. So what's going to happen? That's my, oh my gosh, I can make it cooler. My randomization. Right? Don't quit my day job. Is that what people are saying? Maybe. So now I'm going to randomly assign them to 2 groups. So let me see. I actually did do a randomization on. So I have observation 5 to 10, 9 and 7. So they're going to get the chemical treatment. This second group's going to get nothing. So everybody else. So 1, 3, 4, 6, 8. And then we're going to go ahead and compare results. Drawing this part's not quite as essential, I think, but the idea is I took those 10, I randomly assigned half into each. And depending on what the experiment is, you might decide I really want them to be unequal halves. Maybe I want to have, more in the treatment group than the other. It totally depends on what the goals of the experiment are. And not only that is how many participants that you are able to get. Because if it's extremely difficult to get participants, it might impact like how you weight them, like as far as like assigning them to groups. So then another one that we have is completely randomized block design. So this is when we have some sort of characteristic that we want to make sure we account for. It's usually not what we're interested in actually observing, but we need to account for it. So we group them into blocks. So based on some sort of unavoidable characteristic. Maybe I have, left-handed folks and right-handed folks. I don't know. Of course, people are more complicated than that. Then you randomize once you've separated them into groups. So looking here, we have circles and triangles. So what we did is we separated them into circles and separated them into triangles. And then randomize in each block. So I'm going to randomly assign half in the first block to the treatment 1, half in the first block to treatment 2, and then compare. And then I'm going to do the same thing for the triangles and compare. And this way we can get at the impact of the treatment while still accounting for whatever second characteristic that is. So a lot of times this shows up on plots of land. Another really common place that blocks show up are paired designs. So like when you have matched pairs designs, this is a very, very common place that this shows up. So for example, I participated in, and it was very smart, place where I went to Montana State University, and they had this science lab right across the street from the university. And they would offer whoever participated in studies, I don't know, anywhere from like, $50 to, $700 to participate in studies. So I participated in one, well, more than one, but what happened was they wanted to test like an old ink versus a new ink on skin. And so they randomly assigned my left arm to get one of the inks, and then they randomly assigned my right arm to get the other ink. And then they compared. So I was A block. So because the way my skin reacts on my right arm is probably related to the way my skin reacts on my left arm. They kept those two observations together. I was my own block. So this is a really common place you see blocks, is matched pairs, but there are other instances as well. So absolutely you want to randomly assign within block to avoid confounding variables. So you want to make sure that the impact you're seeing is not these blocks making the difference. You want to make sure it's actually the treatment making the difference. So you do want to make sure you randomize once you separate the blocks. Absolutely. So confounding variables, they're going to be variables that have an impact on the response, but you cannot separate the effect of the confounding variables like from the treatment, which is really problematic. You're like, oh, this is related. Oh, but this is related to it too. You really can't adequately separate the effect of the two, and it happens more often than you think. It's a bummer, but yeah, you want to do what you can to account for those. You don't want to have confounding variables impacting your results. So we have this grass example. Super exciting, right? So we have a farmer. They have two types of grass, and so they have Kentucky bluegrass and Nutri-Green. So I showed pictures here because, you know, I just totally know my grasses. My best friend actually can talk to you like all day about grasses and soils and stuff, but it's not my jam. So they have these two types of grass and they have two types of fertilizer. Specifically, they're interested in looking at the impact of the fertilizer. So they have Turbo Grow and Nutri-Green, which totally sound like real names, right? And they want to figure out, okay, well, let's, assign Turbo Grow to half and Nutri-Green to half. They have the Kentucky bluegrass is broken up into 4 plots. They have the ryegrass is broken up into 4 plots, and they assign, so we have 8 plots total, and they assign, see this orange is, they assign the 4 plots of Turbo Grow there, assign the 4 plots of ryegrass there. So we want to know, after a few weeks, the ryegrass is growing a lot faster than the Kentucky bluegrass. Does this tell me anything about the fertilizer specifically? Can I say, oh, it's the Nutri-Green? So I'll give you all a second to look at that. I wish I had like elevator music. I could probably insert some. So looking here, important things to note is I have these 2 fertilizers, but did I see the 2 fertilizers in both types of grass? And the answer is going to be no. This is problematic. I don't know if it's because the ryegrass grows better, or if the Nutri-Green makes it grow better, or if it's a combination. I have no way of knowing. That's a problem for me, especially if I'm trying to figure out if Nutri-Green is worth buying more of. So we are not able to actually say that Turbo Grow is less effective than Nutri-Green because we're not sure. Ryegrass goes faster than Kentucky bluegrass? We don't know. It could be that it does, but it could be that Nutri-Green helps. So we're going to end up having to say, sorry, nothing, that the fertilizer type and grass types are confounded. There's no way we can actually tell what's making the ryegrass grow faster. Is it the fact that it's ryegrass? Is it the fact that we had the Nutri-Green fertilizer? Is it a combination? We don't know. So we don't get to say here, which is usually a bummer. Nothing is such a bummer as somebody coming to you with years of data and they want to write up their research and you telling them, no, the way this is designed, this is garbage. I strongly recommend if you're going to do research, reaching out to statisticians like statistical consulting ahead of time, just so quite honestly, you can get it designed correctly. I know that the stats department here at OSU, we do have a service, it's free, where we have grad students in the stats department. They do consulting for free on a quarterly basis. Let me know if you're really interested in it. There's more information, but YouTube video is probably not the spot to put it. So we're still attached to the grass example. So we want to reduce the chance of confounding, so we use a randomized experiment. So there are two different, we have the completely randomized. So this is completely randomized design. So what that means is I took my 8 plots and I randomly assigned which, like I just had it 1, 2, 3, 4, 5, 6, 7, 8. And I randomly assigned 4 of them to get Nutri-Green, and I randomly assigned the other 4 to get Turbo Green. But if you look here, I have my Turbo Green, my Nutri-Green. Kentucky Bluegrass has 3/4 of it is Turbo Grow. 1/4 is Nutri-Green. If I look at the ryegrass, it's the opposite's true. 3/4 are Nutri-Green and 1/4 is Turbo Grow. That's a problem. We want to be very, very clear. Like if we want to account for the effect of the type of grass it is, we want to make sure that each grass, half is Nutri-Green and half is going to be Turbo Grow. So this is the completely randomized block design. So that's like they said, okay, I have 1, 2, 3, 4. They assign half to each. Then for the Kentucky Bluegrass, then the ryegrass, they have 1, 2, 3, 4, and they assign half to each. So if I want to get at the impact of the fertilizer but account for the type of grass, I am going to need to use this completely randomized block design. So it does absolutely matter which of the two it is. You're going to want to make sure that you assign half of each grass to half of all the plots for each grass to each fertilizer. So that should work there. So on to lesson 16. We'll see y'all in a few.